Okay, lecture 5, Calc 4. I continue inverses and algebraic properties of matrices. So there's this theorem, it's important. When we reduce an n by n matrix, it's important to know what happens. What do we get? Now, first of all, I can't remember if I introduced this matrix. It's called IN. It's an n by n matrix. It's called identity matrix with dimension n. It has all ones in diagonal. Everything else is 0. Now, this theorem says when you reduce an n by n matrix, you either get this identity matrix or you have some 0 rows. Okay? So, first of all, if I have a 0 row, then that's it. I have one case. So, I mean, that's it. So, we have a 0 row. It's not an identity matrix. So, let's assume that this does not have a 0 row. So, let me right here assume that RREF of A has no 0 rows. Okay, so let's see what happens if I don't have a 0 row. So what is RREF? We have one leading one. So the first leading one is here, then everything else should be 0. Then I have the second one. If the second row is not 0, then the leading one comes somewhere. If the leading one is not here, say it's here, then the rest of them, the rest of the leading ones end up here at least. So the last row will be 0. If the first leading one starts here, not here, on the second position. Well, let me give you an example of this thing. So if I have a 4 by 4, say 1 0 0 0, then I have 0 0 1 0. The third leading one should be to the right of this one. So the third one should be here, or if it's not 0. Then the last one has nowhere to go. I mean, there is no leading one here, so this will be 0. Okay? So if the second one is not here, then I will get a 0 row. So if the second one is not in the second position, then I will get at least 1 0 row. Now, if I had like 5 of them, I mean, if I had like 5 by 5, then this will be 0 0 0, and the 1 can be here, right? And the last row will be all zeros. Okay, so if I just move this one to this position, then I will have boom, 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 boom. These are the ones end up here. So there is at least 1 0 row. Now, if this 1 is even further, if this 1 is like here, then the second one, that's the only place, and I will get 2 0 rows. So if this moves 1 to the right, I will get at least 1 0 row. 2 to the right, at least 2 0 rows, and so on. So, since I assumed there are no 0 rows, this second one should be here. The second one should be here. Well, the same argument tells me, gives me this, that the third one should be here. Otherwise, I will get a 0 row, and so on. So what happens? It means that all the ones should be in the diagonal position so that we do not get a 0 row. So what happens? In the end, I have all ones in diagonal positions, if I don't want to get a 0 row, and the RREF will be the identity matrix, will be IN. Okay. So if any of those leading ones is not in the diagonal position, I will get at least 1 0 row. So all of them should be in diagonal positions, and that gives me an IN. Okay, now that we know what IN is, and we know what a n by n can lead us, or the RREF of A, let's see what inverse means. So let me erase this. So let's make a definition. Given A, let me write n by n here, then B n by n is its inverse if this happens, if and only if B is IN and BA is also IN. So from either side, it should be IN. Okay? Well, let's see if I can find the inverse of a 2 by 2 matrix. Just by inspection, but just saying, okay, if this is the definition of n by n inverse, then simply using this definition, maybe we can find the inverse of a 2 by 2 matrix. So let's say inverse, let me write this here, AB equals BA is IN. So inverse of a 2 by 2 matrix. Okay, so let's say A is, let's write A, B, C, D rather than A1, B1, C1, whatever, A1, 1. So if this has an inverse B, then B should be okay. A, B, C, D, should I say? What should I call this thing? E, F, say G, H. Okay, then I have A, B should be IN. So let's find A, B. And this should be 1, 0, 0, 1, right? So let's multiply this thing. So this time this will give me AE plus BG, AE plus BG, then AF plus BH, then CE plus DG, then CF plus DH. 1, 0, 0, 1. Okay. So I think if I use the A1, 1B, oh, let's see what happens. That would, I mean, I know what I'm doing, but you might get confused then. So here I have this, AE plus BG should be 1. 2 matrices are equal when the corresponding entries are the same. So AF plus BH is 0, then the third one is CE plus DG is 0, and the last one is CF plus DH is 0. So what are the unknowns? Unknowns are E, F, G, H. And A, B, C, D are known. So we have 4 equations in 4 unknowns. This one should be 1, I guess, right? The last one should be 1. So I have three equations or four equations and four unknowns, and if I solve that, I will get E, F, G, H. Now I'm not going to do that, but the only thing is, just imagine I have just 2 by 2, and if I want to use that definition to find the inverse, I have to solve a 4 by 4 equation, 4 equations and 4 unknowns. Now, just imagine if I had like a matrix with 100 by 100, that 100 by 100 would be 100 squared, right? 100 squared. So for each entry, if I have 100 by 100, 100 by 100 has 100 squared, that's 10,000 entries. So I have to solve 10,000 equations in 10,000 unknowns. So there should be a different way to do that, rather than just solving an equation or system of equations like this. So, now I will write the inverse of this for you, and we can check. In fact, this one is the only one that you should, well, if you have an exam, not an online exam or home exam, you have to remember this thing. But anyway, so let A, B, C, D. Well, I'm not going to look at this thing, but let me see if I can remember. So A inverse, if it exists, it should be 1 over A D minus B C. I think, this D goes here and A goes here, and this one will get a minus C and minus B. Let me see if this works. I'm not sure if this works. A D minus B C. I think that's correct. Okay, so well, let me check and see. So this is B, the A inverse. Let's check and see if this really gives me inverse. So A, B, but this is this is just a constant. So I just write the constant outside. Remember, if this B has a constant multiplied by B, you can write the constant outside. That's just a number. So let's multiply this by the other one, C, D, and D minus B minus C and A. So I have 1 over AD minus BC. So that's AD minus BC. So this one is AD minus BC. Minus AB plus AB. You see, this second one is minus AB. Minus AB plus AB. This one will be CD minus CD. And then it is BC minus AD. So AD minus BC. Okay, so multiplying the two, I will get this, and so let's see what happens. I have 0 here. This one is 0. This one is also 0. This one and this one are like this one, right? So I have to multiply. When you multiply a constant by a matrix, you multiply it by every entry. So this one multiplied by every entry multiplied by this will give me 1, multiplied by this will give me 1. Just look, this is the same as this, the same. So the end result is, in fact, where should I write it? So when I complete this thing, I will get this 1, 0, 0, 1, which is I2. Okay, so that B, which has that format, is in fact the inverse of A. And I also introduced a notation here, A with a -1 on top, as inverse. So inverse is denoted by A with -1 on top. Another notation was used a long time ago, so what they decided to use this notation. This doesn't mean 1 over A, please. This, for just numbers, real numbers, that is correct. But for matrices and other things like functions, that is not 1 over something. It's inverse. Now let's see, I said if the inverse exists. So when do you think the inverse does not exist? For what condition? It's in fact this thing. The rest of them is okay. When we multiply two matrices, you can always multiply two matrices if the dimensions are correct. But the only thing that comes into, might make some trouble is this. What if this is 0? So I should assume that this is not 0. Because 1 over 0 is infinity, or let's say undefined or whatever. So this shouldn't be 0. Otherwise I will not get an inverse. And we will see that this is called the determinant. It's the determinant of matrix A. That is in fact next chapter, chapter 2 of this book. Okay, so for 2 by 2, this is what, if I solve that, those 4 equations and 4 unknowns, I would get this. But so we will discuss inverses in this lecture. In fact, then I will give you a method of finding inverse, and I'll also show you why that works. So let me erase this thing. So example, let's just write an example. So if A is minus 2, 5, say 8, negative, say 6, something. Then A inverse, what was that? A inverse was 1 over this times this, minus 2 times minus 6, minus this times this, 5 times 8. Then it was, what was that? I guess this one goes here. So minus 6, minus 2. And this one, I will get minuses in front. And this is 12 minus 40, right? 12 minus 40, that is minus 28. So the inverse is in fact minus 1 over 28 and this. That's okay if you write it like this, but you can get rid of the negative sign. So you can multiply the negative, that's negative 1, multiply by each one of them, you will get rid of the negatives. But that's okay, you can write it like this, that's okay. In fact, it's better to write it like this than putting this here. So, well, you can write it like this, 6 over 28, 5 over 28, then 8 over 28, and 2 over 28. Yeah, I know these are, they can be simplified by 28, so I prefer this one because then if you want to multiply this by something, it's easier to multiply this by something than this. Because these are all integers and it's easier to multiply integers than fractions. Okay. Now, if A n by n has an inverse, then it is called invertible or non-singular. So if A does not have an inverse, then it is called a singular matrix. But anyway, I usually use the invertible than non-singular or singular. But you have seen, you might see that in the literature. So I have written this for you. So Now let's say there's a nice theorem here. If B and C are inverses of A, then B equals C. So what does this mean? It means that inverse is unique. Inverse of a matrix is unique. i.e. inverse of a matrix if it exists is unique. So if you find an inverse using some method or whatever, then that's it. There is no other inverse. That's the only inverse. So let's see if we can prove this together. So what was the definition of inverse? We have to use a definition. So we know that AB is I, N, say. We know that AC is also IN. And we know that the BA is also IN. And we know that CA is also IN. So how can we? Well, it's very easy. I can take one of them, say this one. Okay, I say I know that BA is IN. Let me continue here so everybody can see. So I know that BA is IN. So let's multiply from left, no, from right. Multiply by C. So I have BA multiplied by C, and this is IN multiplied by C. What is IN times C? IN times anything gives that thing back. So IN times any N by N matrix doesn't change that matrix. So this one is just C. How about this one? This one, remember, I can write B outside and then AC. And this equals C. Well, what is AC? Another IN. So this gives me B times, this is IN. IN is C. And B times IN is just B. B equals C. Finished. Okay, so I used this one. I guess I used all of them, right? So I used all these. Let me see, which ones did I use? I used this one, then I used AC equals IN, and yeah, I used this one and this one, and I guess that's it. Yeah. Okay, so if you find inverse using any method, or using like Mathematica or some computer software, then that's it. That is unique. There is no other inverse. And if you cannot find it, then if it doesn't exist, that you cannot. If it doesn't exist, then it doesn't exist. No one can find it. Okay. So now let's see what happens if I want to find inverse of product of two matrices. So given, say, A n by n and B n by n, invertible. Both of them are invertible. Then what is A B inverse? First of all, you might say, does it even exist? Well, if we can find something, then it exists. What do you think? It's interesting when you invert the product of two simple numbers. Let me go to just numbers. So if you have like 2 times 3 and you want to find the inverse, What is the inverse of this? What is the inverse of 2? The inverse of 2, in fact, is 1 over 2. So that's why some students think A inverse is 1 over A. No, it's not 1 over A. Because it's 1 over something when you're dealing with just numbers. But why is it 1 over 2? Well, it's very simple, because this times this is 1. And 1 is like I1. See, 1 is like identity matrix. 1 by 1 identity matrix. So the inverse of this is 1/2, because when you multiply it by 1/2, you will get 1. And this one you said, well, I know from just elementary school, maybe, I don't know when, it's simply 1/2 times 1/3, which is in fact a 2 inverse times 3 inverse. So it's the inverse of this times this, but this doesn't work here. This doesn't work here. Why? Because AB and BA are different. Remember, for matrices, AB and BA are not equal in general. So why this doesn't work here is because AB is not always equal to BA. If AB was equal to BA all the time, then the same thing worked. Okay, so this, I would say that this is in fact B inverse A inverse. So you flip them and invert them and multiply them, and that is the inverse of this. Well, let's see how we can prove this thing. But we have to show that this time this is IN, right? So let's just write it. So 1, I should show that AB times AB inverse is IN. Okay, I should show this thing. So I put a question mark here to say that is this equal to this? So let's see. So AB is AB. I have claimed that this thing is B inverse, A inverse. Okay, let's see if this is IN. So, let me go back again. I have to prove that this thing times its inverse is IN. That's 1. And I have claimed that this inverse is this. So, this means that if I multiply this by this, I should get IN. But let's see. Yeah, I know that I can just remove the parentheses. B inverse, A inverse. B inverse is, so I have A, IN, A inverse, right? This is IN. Then IN times any one of them will give me that thing back. So you can just ignore IN in the middle. Then A inverse is also IN. So it's checked. This one is checked, and you can check the other one, AB inverse. AB should also be IN. So the question mark, and this is the exercise. It's just the same thing. So you can, if you're interested, you can write it, and you see that this happens for this one. So AB inverse is B inverse A inverse. This is an important theorem, and please don't make that mistake. These are not just simple numbers. These are matrices. Okay. And the reason is because this is not equal to this. Well, let's introduce A to power n. If well, let me write n, not. So this is n by n, and A to power m. So how do you define A squared? It's simply A times A. Okay. So this should be A, and n times. And remember, if I multiply A by A, each one of them is n by n, I will get an n by n matrix. So this end result is also n by n. And if I have A and plus B, and they are both n by n, say, and I raise it to the power 2, say. Well, here I have to use the foil, in fact. Why should I use foil? Because I know for numbers there is a rule to find A plus B squared, but it doesn't apply here. So A times A is A squared, A times B is AB, B times A is BA, and B times B is B squared. And AB and BA are not the same, so I cannot write 2AB or 2BA. These two are not the same, so it just stays like this. I can raise it to power 3, and then I have to multiply 1 by 1, so I will get A, B, B, A, B, and things like that. So when you multiply them, don't assume that these are the same. No, they are not the same. Let's go to the transpose of a matrix, A transpose. Remember, A transpose what was what? So if A was Aij, then A transpose was Aji. So if this is n by n, A is n by n, m by n, this is n by n. Now, what happens if we transpose an n by n matrix? It's n by n again. So transpose of n by n is n by n. Now there are some rules, some properties of the transpose. One, transpose of, say, A n by n. So if I transpose this and do transpose again, I will get A back. So transpose is like I haven't done anything. 2 is if I add them and transpose, then it's like A transpose plus B transpose. Or if I subtract them, the same thing happens. And the third one is if I multiply this by some constant, this is constant or scalar, and nothing happens here. So that stays, the k doesn't change, and number 4, which is important, and it looks like the other one, that is A times B transpose. Then that is B transpose, A transpose. So both for inverse and transpose, you have to flip. You have to flip and put that operator on top. So being inverse or transpose, you flip this thing. I'm not going to prove this thing, but you can write it down and see for yourself that this happens, at least for a 2 by 2 matrix. These are easy to understand and even prove, but the last one is not that easy to understand. And one last property, but let me write that number 5 here, which is important. So number 5 is in fact an important one. So what is inverse of A transpose? If A has inverse, then A transpose has inverse too. And the inverse is interesting. It is A inverse transpose. Right? But let's see if I can prove this thing. So So I'm saying that this is the inverse of this. So I should show that A transpose times its inverse, say, is IN. Right? So let's recall something. Remember, A, well, no, that's okay. So let me write something else, not A and B. So I'm using A. So if I have two matrices C and D, remember, transpose of this was D transpose, A, C transpose, right? Now, this is like the C, this is like D transpose, this is like C transpose, right? Okay, so this thing, using that is in fact A inverse times A transpose, right? That is A transpose, A inverse transpose. But this is IN transpose, and IN transpose is simply IN. Change IN. Okay? You can easily prove the other way. A inverse transpose A transpose, then again flip this thing. So that is A inverse transpose, which is again IN transpose, which is IN. So, what does this tell me? It tells me that you can interchange inverse and transpose. You see, you can interchange inverse and transpose. It also tells me that the transpose, if A has inverse, then A transpose also has an inverse. So I'm using the inverse of this thing. So this is the last property, not the last, but anyway, one of the properties of transpose, and transpose is used a lot in mathematics, not just in algebra. So okay. Now, since I still have some time left, let me start another subject. This is in fact where we start, where I will give you an algorithm to find inverse of a square matrix. So remember, square matrix is A by N by N is called square matrix. Why? Because the two dimensions are, they're both N. So when I say square matrix, I mean some N by N matrix. So let's see. So this is the subject, elementary matrices. So what is an elementary matrix? So definition is this. Well, let me say it, then I will write it here. An elementary matrix is this. Take IN and apply one of those row operations, one of those three row operations, then what the result is an elementary matrix. So what were the row operations? Row operations were like multiplying a row by a scalar, say. The other one was multiplying a row and adding to another row, or interchanging two rows. So I can say that an elementary matrix is an elementary matrix is a matrix obtained from IN by applying one of the row operations. And there's another definition. We say A and B are equivalent if A is obtained, or let's say B. Okay. B is obtained from A by applying the row operation. So it means that if I apply so many row operations, they are still equivalent, not just one. So what can I say about elementary matrices? So this means that elementary matrices are, in a sense, equivalent. So it's like I'm dealing with just one matrix. Now, remember, when you apply row operations, if you have a system of equations and you apply row operations, you're changing the system, but you're not changing the answer. So that's one thing behind this, because if you do the row operations, if you apply row operations and you get the RREF, then the RREF makes things easier for you. You can now find a solution easily. So, which means that in a sense, those two systems of equation are equivalent. They're not the same, but they're equivalent, which means they have the same solution. Okay, so let's look at some elementary matrices and also look at one thing, ask one question: do they have inverse? So let's look at some elementary matrices. So I said IN apply some row operation. What are the row operations? Row operations, remember, was say some k times row I goes to row I again, and 2 was row I interchange with row j, and 3 was, but again I used the capital R, that's okay. So it was say k times row I plus row j goes to row j, not row I, but row j. So let's see what happens if I apply this first one to IN. So one, if I say k times row I goes to row I, then it will be 1, 0, 0, and row I, I will get k here, 0, 0, 0, right? 0, 1. So I will get just a k somewhere in row number I. And this is an elementary matrix. Now, what is the inverse of this? It has an inverse. Inverse is simply 1 over k. So if this is, say, an elementary matrix E, then this is the inverse. 1, 0, and then 0, 1 over k. 0, and the last one, 1. So that's E inverse. Just try and multiply these two, and you will get, in fact, this row multiplied by this row, everything is 0, the k multiplied by 1 over k will give me 1. So the result is 1, 1, 1, 1, 1. And if I multiply this one by this one, then I will get 1 over k times k, that is again 1. So either way I will get 1. So this has a nice inverse. It's like multiplying that ith row by 1 over k this time. So its inverse is something similar to itself, or this some similar operation will give me the inverse of this matrix. Now, the other one, let's check this row I and row J. I will give you examples in the end. So, number 2, row I and row J. Row I goes to row J and row J goes to row I. So what happens? So the E will be like this. So I have say 1, 0, 0, and row I will be at J. I have 1 here, the Jth column, and then if this is J, this is I say. Then I have 1 here, then 0, 0, and 0. You see the I, this I was here, so it goes here. And the Jth row, the J, I was at the row J, then it comes here. Okay, so what is the inverse of this?
Here's the definition of end result, the final result or outcome of an activity or process.
Okay, so that is in fact the same thing. So do the same thing and it goes back. So if you apply the same thing, it goes back, right? So the inverse of this thing is itself. Yeah, right. So the inverse is itself. This is an amazing situation that a matrix is its own inverse. So inverse is the same thing. Same. Right? And you are getting some idea here that it's like when you do some row operation, it's like multiplying a matrix by one of these elementary matrices. That is in fact what I'm trying to get to. Now let's see what this third one is. Number 3, multiplying row I by some k and adding to row j. But this is simply you will get. So this is row I, say, and this is row j. So you have 1, 0, 0, 0, and then this doesn't change. But row j, if I multiply this by k, I will get k plus 1. And then 0, and 0, 1, right? So I will get k plus 1. So this is the E. So what do you think, what should I do to get E inverse, which means I multiply this by what to get E I? So what do you think this is? Well, if I apply the same thing, except this time multiply by minus k, I will get I. So E inverse is this. Minus k plus 1. Okay, well let me, I'm not sure if I think that's correct. So let me put a question mark here and you check this thing and see if that is in fact correct. But anyway, so what I'm trying to say is that if applying a row operation to a matrix is like multiplying that matrix by an elementary matrix with the same property. So if I want to multiply a row of any matrix n by n by k, I multiply that by the first matrix, the E that I found by multiplying it by K, multiplying row I by K. Now I will come back to this next time, just introduce elementary matrices, and we will see how these matrices work. Okay, so